here and take its derivative, we...
Okay, this is part 3 of me doing my homework. Wait a minute. Where's my pen? Oh, right. Where am I now?
delta function to get it into a form that is easy to integrate over. Specifically, the integral that we need to perform is this one. Using normal delta function...
Okay, we are in that part. Using normal identities, we can rewrite the delta function the following way that makes the integral easy to do. Normal identities. My question is, what is normal identities? Like, is that even a thing? No, it's not. Let me ask this guy. What is normal identities? Scaling property. seems different in here. Please, I don't understand. The cross-section formula contains the integral. Yeah, alright. Yeah, that's correct, yeah. Here is the magnitude of the outgoing particle 1. Magnitude of the momentum of outgoing particle 1 is the energy of outgoing particle 1 is the energy of outgoing particle 2 dependent on K1. I don't know how it can be independent like that. This enforces energy conservation. The aim is to simplify this integral using the properties of the delta function. The delta function ensures energy conservation. Are fixed incoming particle energies, which depends on individual momentum conservation. Since the delta function ensures a specific relationship between these terms, we can reexpress it as a function k1 alone. To do this, note that depends on the k1. Okay, substituting ak1, we can write. Okay, I understand until this part. This isolates k1 as a variable interest for the delta function. Delta function properties. This is a property where fk1 is this k10 is the root of goes to 0. What is root? Which is the physically allowed value of k. I don't understand. Derivative of this. Okay. Differentiate this. Differentiate it. Differentiating this becomes this. Oh, you can do that. Oh, you can do that? You can reply it like that? Wow. This is getting interesting. The rest becomes 0, right? Yeah, the rest becomes 0. Only this one's left. The term comes for the dependence of it on the one, but for simplicity we focus on its magnitude. What do you mean? performing the integral. You know, I hate my hair if it's clean like this. I just I just finished using shampoo and my hair is so hard to shape. The delta function now simplifies the integral. When integrating over k1, the delta function selects the value k1 equals k0. So why is this? What?
Identities, we can rewrite of this argument of the delta function, which I've called f function, or
Oh, okay. How is this came into being? Oh, it's supposed to be 1, right? It's supposed to be 1. No, it's not 1. Oh no, if you like integrate a function with a delta function, it will become that function itself. So it will become this value, which is, you know, equal to this value, which is, you know, becomes this. But where is this one came from? Oh, nothing. It's just the fact that this is equals to just it came from here. Okay, okay. I need you to yeah to explain for me that one. What does it mean when it's the root? What does root of mean? Explain. Where's my response? Wait, what? Why does it take so long? Set. I'm too lazy to think right now. Why don't you just... No. I think... Oh, it continues explaining. Oh, anyway. Okay. Explain me this. Oof. This function comes from the delta function that enforces energy conservation in the integral. We rewrite it in terms of Q1, giving this equals this. This function describes the mismatch, if any, between the total energy of the initial particles and the total energy of the final potential. Why do we care about this? The delta function ensures this is zero. Oh yeah, that's correct. The condition of this equals gives a specific value of K1 that satisfy energy conservation. The root of the equation of this equation. What does that mean? Oh, it's the value of K1 if all of this is equals to zero. This means the physical magnitude of the outgoing that satisfies energy conservation. When integrating with the delta function, it forces K1 to take this specific value. The delta function property, this property, requires us to compute the derivative of fk with respect to K1. The differentiating become like that. The term comes from Najib K1. Why don't we just remove the M1? Because the mass of a photon is zero in this case, right? The delta function essentially collapsed the integral over K1 by picking the value the energy conservation equation where n is function of K1. The root of the percent physical momentum magnitude of the outgoing particle 1. Alright. How can I delete this? Okay, if that's so, I think I kinda understand this. The delta function now simplifies the integral. When integrating over k1, the delta function selects the value k1 equals to k0. So, okay, I don't understand where this. So annoying. Thank you. Start with the delta function property. This equals to this. Oh yeah, I think I understand. Right. K1 is the rest of the integral. In this case, it's the root of right.
Or the actual value of k1. Because of the delta function, the integral simply forces this relation to be true, relabeling the actual momentum k1 naught with the symbol previously used to represent the integration variable to make things simple, and then continuing the calculation gets us to this. If we actually look at the form of this f function here and take its derivative, we find this value. For it. As I described above, the superscript on the differential is usually dropped. It was useful to keep track of things while we were doing the integration, but it is no longer needed, so we will drop it and return to the standard notation.
I'm scared. Help. There's still a lot of it. Oh my god. Oh my god. This takes months. And not only that, there are two other videos explaining. There are still two videos that I need to watch explaining the origin of some formula, the general cross-section formula. Actually, in this video, the formula for the cross-section is known. I have to prove it, so I have to watch other videos to see how it get proved. And also, there's another video that talks about how we find the Feynman diagrams. There are a lot. I think I don't understand. There is something that I don't understand. That looks awful. I don't think that's the answer. I mean, look at this. It's different, right? It's supposed to be looks like this. It's not like that. Okay, I will ask him about that later. Whew, I don't understand. Maybe I need to see some delta function of identities or something. I think I kinda understand it now. I kinda understand it, but whether um yeah, I mean technically I understand it now, but I just wanna make sure whether my understanding is correct or not. Yeah, I think it uses this technique, right? I kinda understand it now. Yeah, so actually it doesn't use this one, but it it uses this one, this this one, and then it uses this technique, and I just want to make sure that this formula is actually exists. I mean, this 1/f derivative is actually exists. That's my only problem. Whether this one, right, whether it actually exists. You know, I I agree with this one. I agree with it. I mean, it's true, but like this one, is it really true? Well, this one, that one, I have to check. Yes, it is. Look at that. That's really beautiful. It does exist. Wow. What is that? E. What is that? What is that for? So we have to keep this formula and this formula. How long have we been streaming? Almost 1 hour. Uh, you know, I wanna do something. So let's end it here. I will end it here, and I will come back in a minute or maybe